So these have a closer spacing of the vibrational levels. And the ground state, in general terms, has a larger spacing of vibrational levels. And both for the excited state and for the ground state. By the way, there can be many excited states, not just one. Levels get closer together as the V quantum number increases. And this, the reason it does is anharmonicities and centrifugal distortion. No longer a Hooke's law spring. So if molecular vibrations acted like Hooke's law springs, F equals kx, potential energy is 1/2 kx squared, you'd have this ladder of equally spaced levels that would go on forever, both in the ground and the excited state. But as you pull the molecule further apart to where it's trying to stretch apart, it no longer behaves like a Hooke's law spring. The levels come closer together, and in the end, they're essentially infinite together. Okay, now all of this has some significant spectroscopic consequences. Okay? For the excited state, the levels, the lowest level I'm going to be able to hit, probably, I might be able to hit this level. So I might be able to hit, basically the bottom of this has to overlap with this. So the spectrum I would get the emission or luminescence will look like this. Wavelength is increasing this way, energy is increasing that way. So the longer the line, the more energy, the less wavelength. So basically, in emission, at fairly low energy, I would get four lines, and maybe I could get a fifth line. We'll do a fifth line like this, and maybe a sixth line just right on the edge, and maybe this one right here. Maybe if we're lucky, right there. So we get a whole series of lines. But what we actually see is this. So this is a vibronically broadened emission spectrum. Now, what will happen when I go the other way? Well, now I start stepping up like this, and I get a whole series of lines going up. And guess what? I get another transition with a bunch of lines like this. So this is the absorption spectrum. Now, it turns out that most routine plots of these are the other way from what I've said. So this is a less common plot. The more common plot is to run increased wavelength to the right and increased photon energy to the left. This is more common. Okay, and in fact, it is this lowercase, this is what we have drawn in the lowercase. So, this is the more common case. Now, this is absolutely fundamental, and we can learn a lot just stopping right here. We instantly understand why molecular spectra are very broad, typically, compared to atomic spectra, which have all these sharp lines. The answer is that atoms are combined into molecules, and we can generalize beyond the diatomic molecule, but the diatomic case is pretty good. The energy is going to be a function of internuclear separation, and there are going to be vibrational energies embedded in that internuclear separation. And we can activate all these vibrations as we go from one step to the other. And we can get all these bands. Now, interestingly enough, if we're doing absorption, if we're going up, we potentially can measure the vibrational energy levels of the excited state in absorption. Now, what about going down in emission? We're going to get the notching pattern due to the ground electronic state. So it's backwards, isn't it? As you go down, you get one set of states. As you go up, you get another. Now, we're trying to draw too much on this diagram. What I need to do is slow it down and draw the absorption and the emission cases more carefully. Okay, so close up of vibronic absorption. So these are two electronic states. Here's the energy, here's the internuclear separation R. The ground state always has wider separated energy levels, so we'll kind of show those. And the excited state has energy levels that are much closer together generally. So I'll show those like this. So that's a very realistic picture. The vibrational quantum numbers start at 0. And now we're going to assume that all the transitions start from the bottom, so we can go from here to here, here to here. Do you see what I'm doing? I'm climbing that ladder of excited state energy levels. See how that's going? And so this is absorption. It's called vibronic absorption, a combination of vibration and electrical. We could hit hundreds of energy levels like this. Now, what would the spectrum look like? So our spectrum, if we have energy going this way and wavelength going that way, we had the lowest energy one first. So we have 1, 2, 3, 4, 5, 6 bands. And the overall band shape would be like so. And these would be 1, 2, 3, 4, 5, 6 going this way. So we're plotting absorbance. So this is an absorbance or UV visible spectrum. Now you might ask, what about the intensities? The length, in the upper figure, the length of the arrow tells me the energy of the photon. What are the lengths of the arrows, or the lines here? And those are intensity things. And the basic idea is how well aligned is this with this? In other words, the better it's aligned, the more intense the line. So intensities are determined by the lineup of the ground with the excited state. So the one that has the best lineup, and that's the formal term for this, is the Franck-Condon factor, which we will get to. Okay, so that's the close-up of vibronic absorption. And kind of the mystery is, why are some lines more intense than the others? And the answer is, the two electronic states have to be well aligned for there to be significant intensity. We do this with an integral called the Franck-Condon factor, which we don't want to introduce right now, but we'll talk about later. Okay, that's absorption. What do we do about emission? And notice the fine structure, before we get on to emission, the fine structure is that imposed by the excited state. We're climbing this ladder in the excited state, and so the spacing between the lines here is that of the excited state. Well, now we want to go the other way. We want to emit light, and we want to see what happens, and everything's going to turn around. So we were trying to do this on one diagram. It's really helpful now for us to split the diagrams like we've been doing. Let's make this a little bit closer. Something like this. Okay. So we'll have the same kind of a deal. So the wider space levels down here, and we're just kind of showing only part of the wells, the potential energy well, as it is called, then much tighter up here. And now in the excited, we get the molecule excited, and we still have V equals 0, V prime equals 0. So it's typical for the luminescence to start at the lowest vibrational level. So we're going to have this, and this, and this, and this, and this, and this. And we have another spectral plot, and we're going to do, as is traditional, energy increasing to the left and wavelength increasing to the right. We're going to have luminescence intensity. We're going to number these. 1, 2, 3, 4, 5, 6, going in terms of increasing energy. And let's say 3 lines up about the best, so it's 1, 2, 3, 4, 5, 6. And we have this thing. And which state is the fine structure? Fine structure is imposed by what? Everything's coming down. We're going on a down ladder where the gaps in the ground by spacings of ground state vibrational energy levels. Okay? So the ground and the excited states are similar, only the emission gets what's down in the ground state. Now, if you're to plot these two on the same graph, what would they look like? And here's an interesting answer. If you do atoms, like if you do sodium atom, sodium emission and sodium absorption will be at the exact same wavelength. if you don't have any relativity, if things aren't receding. It's just in the lab. Sodium emission and sodium absorption, identical wavelength. Here, it's more complicated. And let me show you why. First of all, what's the lowest energy level here? I'll indicate it in red. It's from V equals 0 to V prime equals 0. This is the so-called, this is the 0, 0 lowest energy transition. What's the lowest energy one here? Or the highest energy ones, excuse me. It's this one. From V prime equals 0, so this is the highest energy emission line, and this is the lowest energy absorption line. And this, of course, is a transition. Okay, now, do you notice something about the highest energy emission line and the lowest energy absorption line? There's something really important about those two.
Exact same length.
They're the exact same length. So the 0, 0 transition in absorption and in emission are the same. But all the other ones are not. Now, look at just look at these arrows compared to these arrows.
The transition is getting higher.
These are lower in energy. This gets back to what you were asking me at the beginning of the hour. These are lower in energy. The highest energy of this one is equal to the lowest energy of that one. So, if I were to put these two together on the same graph, okay, and let me see if I can come up with a different color.
Absorption will be much higher energy altogether.
Right, let's say this is the emission, but I'm now going to superimpose this absorption on there, and I'll do it in red, okay? The 0, 0s will be the same.
Okay.
And then the absorption ones are going to be much narrower. There's the 0, 0. So the absorption is at higher, remember energy is going to the left in the common convention. The spacings of the absorption are going to be closer together because the excited vibrational levels are closer together. And the absorption and the emission, the spacings are going to be further apart, all things considered, and everything's going to be shifted to lower energy. So here's a huge difference between atoms and molecules. Atoms, absorption and emission, are identical. Molecules, and we're considering the same two states, only the 0, 0s will be the same. And the absorption will go off to the high energy side, but we'll have spacings of the excited state. The emission on the low energy side will have the vibrational spacings of the ground state. We have covered an incredible amount of material today. Wow, I mean, this is really cool. Now, let's go back to what you were asking about. As I understand it, you were kind of saying, well, isn't emitted light typically lower in energy than absorbed light? And here we're seeing, for the very same electronic state, with vibration superimposed, because the higher energy lets us get to the vibrations. For the very same states, the absorption is always going to be higher in energy on average than the emission. And if you're looking at the peaks, they're going to be considerably separated from one another. Now, if you go to other states, it even gets bigger, but for the same pair of states, absorption higher in energy, emission lower in energy, always for molecules. Just, there's no getting around that.
Quick weird question. So when you're not dealing with electrons at all, and we're just talking about vibrations, and
you can't do that because chemical bonds are made of electrons, and you vibrate that molecule, you're knocking electrons around.
Okay.
So you can't not fool with the electrons in a molecular vibration.
Okay.
You are fooling with them. You're just doing it more subtly.
So when you think of an emission of a photon for vibration, for dealing with only the vibration emission, what does that look like molecularly, like compared to? Because I'm like in my head,
the molecule's vibrating like this in one state, and it's vibrating like this in another one. And remember, you can access molecular rotations, microwave. Infrared has enough energy to access molecular rotations.
Okay.
So you're going to have rotational fine structure superimposed on molecular vibrational spectra.
Because the only thing I'm getting confused over, and it's probably a simple concept, is in my head I'm seeing absorption. I'm seeing absorption of a photon, and excitation of
an electron
popping up, popping back down, which causes emission of a photon.
That's a good picture.
So what about when you're vibrations? I'm not seeing like a jump of an electron and a jump down.
But you are moving. You're obviously, if you're moving the nuclei back and forth, you're moving the electron pair.
And it's still at a quantitative level, so it's vibrating at a certain thing, vibrates at a specific level.
It vibrates here, then it vibrates there, and there's an energy difference between the two.
Okay.
That is kicked out.
Got you.
Okay. So we now understand why atomic spectral lines are sharp and why molecular, if we do UV visible or visible luminescent spectroscopy, we are going to have fine structure. Or we may not see the fine structure, we may just have a pair of broad bands. That's very common too.
And in luminescent spectroscopy, do you have to have the absorption over visible light? Because
no, the absorption could be in the UV,
the ultraviolet.
Yeah,
it can't be infrared though.
It can't. Okay, you can have an absorption in the near infrared and an emission in the far infrared. You just have to have the situation where you have a little bit more energy in than out.
Okay.
We got that backwards. More energy in than out. Yeah, so in other words, in biology, it's very common to excite samples with ultraviolet light. And many biological samples are white or colorless. They don't absorb in the visible. But you hit them with ultraviolet light, and they will emit light that's in the visible.
Yeah.
That's really common, is it not, in biology? You shine a black light on it, and it lights up with all these pretty colors. That's what's going on. Okay. Now, this is a very logical transition point for us to actually consider the measurement of spectra of molecular systems. Okay? There are two spectra that I typically have people measure, and we're going to start out with absorption spectra. I'm not going to do the emission with the absorption to start with. We're going to start out with absorption. We're going to see this process where we interrogate the vibronic levels of the excited state. And the two chemical species that we're going to work with are potassium permanganate, which has a lovely vibronic progression that you can see quite readily. Potassium permanganate and benzene, let's say, and cyclohexane. And you'll see the ring stretching vibrations of benzene. And for potassium permanganate, you'll see the totally symmetric breathing vibration. MnO4 is a tetrahedral anion. And so you'll get the ring breathing vibration. And you'll get this in permanganate, and you'll get the benzene breathing vibration where all the atoms come out and in benzene. So you'll have two classic examples, one from organic chemistry and one from inorganic chemistry, and we're going to measure those in. So we're just going to be doing this one today. Okay? And then in our next class meeting, we are going to look at ruby, which is has a very beautiful and spectacular absorption and luminescence spectrum. We're going to see something really interesting in ruby, because we're going to access some different states and see both the absorption and the luminescence. Will be pretty cool. All right. So the task before us at this juncture is to get a drop of benzene in a cuvette of cyclohexane. I mean, you don't need much.
Gotcha.
I mean, not much at all. Now, before we head down to the lab, I need to ask you guys a couple questions. We want to be deliberate, focused, and systematic regarding getting all these tests and assignments in. So what I'd like to do is start working on those through either parts of the lab period and or parts of this this period. So what that entails for you gentlemen is starting to systematically go through these tests and make sure that you have questions for me that I can address.
Okay.
And that we can, in dialogue, just cut right through this stuff and get it done as we have an obligation to do. So my guess is with, getting grad school and getting engaged and all this, and you trying to finish things up, that probably sitting down with those exams has not been on the front burner.
Yeah.
Is that a
pretty accurate?
Okay, so but we're going to move it to the front burner. I went, and this is an assignment. I want you to look at the first test.
Okay.
And I want each of you to have two